Welcome to this problem walkthrough. Today, we're diving into problem number 1525, number of good ways to split a string. We'll explore the problem, break it down step by step, and walk through various approaches to find an optimal solution. Let's get started. In this problem, we are tasked with determining the number of good splits in a given string S. A split is defined as dividing S into two non-empty substrings, left and right. For the split to be considered good, the number of distinct characters in left must be equal to the number of distinct characters in right. Our goal is to return the total count of such good splits. The string S will consist of lowercase English letters, and its length can range from 1 to 100,000 characters. The output of the problem is a single integer, indicating the number of good splits that can be found in the string. For example, let's consider the string S equals Akaba. The output for this input is 2, because there are two good splits. Let's break it down step by step. When we split the string at various points, we observe the number of unique characters in the left and right substrings. For instance, splitting at left equals AAC and right equals ABA gives both substrings two unique characters, which makes this a good split. Similarly, splitting at left equals AKA and right equals BA also results in two unique characters on each side, making it another good split. In total, there are two such splits. Now, consider another example where S equals ABCD. Here, the output is 1, as there is only one good split possible. Let's evaluate the splits. Dividing into left equals AB and right equals CD results in both substrings having two unique characters, making it a good split. However, other splits, such as left equals A and right equals BCD or left equals ABC and right equals D, fail to meet the criteria because the number of distinct characters on each side is not equal. Thus, there is only one valid split in this case. Next, let's analyze the string S equals AAAAA. The output for this input is 4, and the reason is quite interesting. In this case, every split is good because the string contains only one distinct character. Whether you split it at left equals A and right equals AAA, or at left equals AAA and right equals A, both sides always have one unique character. This symmetry results in every possible split being good, and with 4 total splits possible, the output is 4. Finally, let's address some constraints and edge cases. For very short strings, such as S equals A or S equals AB, no good splits are possible. This is because the string is either too short to form two non-empty substrings or because the unique character counts in the two parts cannot match. Additionally, for strings with all identical characters, like AAAA, every split is good, as noted earlier. And for strings with no repeated characters, such as S equals ABCD, there is typically only one valid split where the unique character counts are equal. These scenarios help us better understand how the problem behaves under different conditions. To approach this problem, we start by considering a brute force solution. The intuition here is straightforward. We iterate over every possible way to split the string into two parts. For each split, we calculate the distinct characters in the left and right substrings. If the counts of distinct characters in the two parts are equal, we count it as a good split. The steps involve iterating through the string, splitting it at each index, and using sets to determine the distinct characters in each part. While this approach is simple and easy to understand, its computational cost is high. Calculating distinct characters for each split takes O(n), and since there are n possible splits, the total time complexity becomes O(n squared). This makes the brute force approach impractical for larger strings with high constraints, such as when n exceeds 10,000. The simplicity of this method is offset by its lack of scalability, which creates the need for a more efficient solution. To address the inefficiencies of the brute force method, we can use an optimized approach that calculates distinct character counts dynamically as we iterate through the string. Instead of recalculating counts from scratch for each split, we maintain two running counts, one for the left substring and one for the right substring. This is achieved using two frequency maps, left_frequency and right_frequency, which track the character frequencies in the respective substrings. Initially, we populate right_frequency with the frequencies of all characters in the string. Then, as we iterate through the string, we incrementally update both left_frequency and right_frequency. For each character, we add it to left_frequency, updating the distinct count if it's a new character, and remove it from right_frequency, updating the distinct count if its frequency drops to 0. By comparing the counts at each split, we can efficiently determine if it's a good split without recalculating everything from scratch. This avoids the redundant work present in the brute force approach. The optimized approach significantly reduces complexity compared to the brute force method. The time complexity is O(n), because we traverse the string once to initialize the right underscore frequency map and then iterate through it again to update the counts in left underscore frequency and right underscore frequency. The space complexity is O(1), assuming a fixed character set like lowercase English letters, as the size of the frequency maps remains constant regardless of the input size. This makes the approach highly efficient and scalable to larger inputs. While it's slightly more complex to implement than the brute force solution, the gain in efficiency is substantial. By eliminating unnecessary recomputation, this method achieves linear time complexity while maintaining correctness, making it well suited for handling constraints where n is very large. Given the trade-offs, the optimized approach is the chosen strategy for solving this problem. While the brute force solution is more intuitive, its O(n²) complexity makes it impractical for larger strings. The optimized method, on the other hand, leverages frequency maps and dynamic counting to achieve a significant improvement in time complexity, reducing it to O(n). The key insight here is recognizing that distinct character counts can be maintained dynamically as the left and right substrings change. By tracking these counts incrementally rather than recalculating them for every split, the approach eliminates redundant work. This balance of efficiency and scalability makes the optimized approach the best choice for this problem, especially under the given constraints. In this problem, we're tasked with determining the number of good splits for a given string S. A split is considered good if, at the split index, the number of distinct characters in the left substring is equal to the number of distinct characters in the right substring. To solve this, we can start with a brute force approach. Here, we iterate through the string and check every possible split point. At each split, we count the distinct characters in the left and right substrings. While this is straightforward and guarantees correctness, it is computationally expensive due to the repeated counting of distinct characters. To begin, we initialize a counter good_splits to 0, which will keep track of the valid splits we encounter. The string S has a length n, and we will explore all potential split points between the indices 1 and n1. To implement the brute force approach, we loop through all potential split points in the string. For each index I from 1 to n1, we divide the string into two parts, the left substring, which spans from the start of the string to index I1, and the right substring, which spans from index I to the end of the string. Once the string is split, we use Python's setData structure to count the distinct characters in each substring. The number of distinct characters in the left substring is calculated as len, set, left, and for the right substring, it's len, set, right. If the counts of distinct characters in the left and right substrings are equal, we increment the good_splits counter. Finally, once we've checked all possible split points, we return the value of good_splits as the result. The brute force approach works because it explicitly calculates the distinct character counts in the left and right substrings for every split, ensuring correctness. However, this method has significant limitations. At every split point, we recompute the distinct character counts from scratch. If the string has a length n, and the average length of the substrings is approximately n/2, the time complexity becomes O(n²)*m, where m is the average number of unique characters in each substring. This makes the approach inefficient for longer strings. To address this inefficiency, we can optimize the solution by pre-computing the distinct character counts for all prefixes and suffixes of the string. By doing so, we can dynamically track the distinct character counts without recalculating them repeatedly, which drastically improves performance. To optimize the solution, we use prefix and suffix arrays that allow us to compute distinct character counts for any split point in constant time. The first step is to initialize two auxiliary arrays, prefix_count, which stores the number of distinct characters from the start of the string up to each index, and suffix_count, which stores the number of distinct characters from each index to the end of the string. To build these arrays, we use two sets, one for the prefix and one for the suffix. These sets dynamically track the distinct characters seen so far as we iterate through the string. For the prefix_count array, we traverse the string from left to right. At each step, we add the current character to the prefix underscore scene set and update the prefix underscore count array at the current index with the size of the set, which represents the number of distinct characters encountered so far. Similarly, we construct the suffix underscore count array by traversing the string from right to left. We use a set called suffix underscore scene to track the distinct characters encountered as we move backward through the string. At each step, we add the current character to the suffix underscore scene set and update the suffix underscore count array at the current index with the size of the set. Once both prefix underscore count and suffix underscore count are built, we can efficiently count the number of good splits. We initialize good underscore splits to 0, then iterate through the string from index 0 to n2. For each split point, we compare the value of prefix underscore count, I, with suffix underscore count, I plus 1. If they are equal, it means the split is good, so we increment the good underscore splits counter. After completing the loop, we return the value of good underscore splits as the result. The core of the optimized approach relies on two key data structures, prefix and suffix arrays, and sets. The prefix and suffix arrays store the pre-computed number of distinct characters for each prefix and suffix of the string, respectively. This removes the need to recalculate distinct character counts repeatedly, saving significant computation time. The sets are used during the construction of the prefix and suffix arrays to dynamically track the distinct characters encountered as we traverse the string. Sets are particularly efficient for this purpose because they allow for constant time operations for inserting and checking elements. Together, these data structures enable us to achieve the desired result with far greater efficiency than the brute force method. Analyzing the complexity of the optimized approach, we see significant improvements. Constructing the prefix underscore count and suffix underscore count arrays requires a single traversal of the string, with each character being processed in constant time. This results in a time complexity of O(n) for building the arrays. Comparing the prefix and suffix counts at each split point also requires a single pass through the string, leading to an additional O(n) time complexity. Overall, the total time complexity of the optimized approach is O(n). For space complexity, the prefix underscore count and suffix underscore count arrays each require O(n) space. The sets used to track distinct characters have a maximum size bounded by the alphabet size, which is constant for most practical scenarios. Thus, the total space complexity is also O(n). When implementing the algorithm, it's important to consider edge cases. For instance, if the input string s is empty, there are no possible splits, so the result is 0. Similarly, if the string contains only one character, no valid splits can be made, resulting in 0 as well. When all characters in the string are identical, every split will result in equal distinct character counts of 1, so the result is n1. Conversely, if all characters in the string are unique, no split will result in matching distinct counts, and the result will be 0. For strings with a mix of repeating and unique characters, the algorithm handles these efficiently, ensuring correct results regardless of the character distribution. Here, we start by defining the number splits function, which takes a string s as input. To solve this problem, we use two dictionaries, prefix underscore count to track the frequency of characters in the prefix of the string, and suffix underscore count to track the frequency of characters in the suffix. First, we populate suffix underscore count with the frequencies of all characters in the string s. This gives us a complete picture of the character distribution before any splits. Next, we initialize several variables, good underscore splits to count the number of valid splits, prefix underscore unique to track the number of unique characters in the prefix, and suffix underscore unique to track the number of unique characters remaining in the suffix. The value of suffix underscore unique is initially set to the total number of unique characters in suffix underscore count. Now, we iterate through each character of the string. For each character, we add it to prefix underscore count and update prefix underscore unique if it's a new character in the prefix. Simultaneously, we decrease the frequency of the character in suffix underscore count. If a character's frequency in suffix underscore count drops to 0, we remove it from the dictionary and decrease suffix underscore unique accordingly. At this point, we determine whether the current split is a good split by comparing prefix underscore unique and suffix underscore unique. If these values are equal, it means the number of unique characters in the prefix matches the number of unique characters in the suffix, so we increment the good underscore splits counter. This process continues for each character in the string, ensuring that all possible splits are evaluated. Finally, once the loop completes, we return the total count of good underscore splits as the result. This approach ensures that we efficiently calculate the number of good splits while maintaining clear and concise logic. Here, we begin by importing the necessary libraries and defining our solution class. Within the number splits method, we first initialize two hash maps, prefix count and suffix count. These will be used to track the frequency of characters in the prefix and suffix parts of the string as we iterate through it. Next, we populate the suffix count map with the frequency of each character in the input string S. This ensures that before we start splitting the string, we have a complete count of all characters in the suffix. We also initialize a counter, good splits, to track the number of valid splits, and two variables, prefix unique and suffix unique, to store the count of unique characters in the prefix and suffix respectively. Initially, prefix unique is set to 0 since no characters are part of the prefix yet, while suffix unique is initialized to the total number of unique characters in the string. Now, we enter a loop to iterate through each character in the string. With each character, we first update the prefix count map. If the character is not already in the prefix, we increment the prefix unique counter to account for this new unique character. Then, we increment its count in the prefix map. Next, we update the suffix count map by decrementing the count of the current character. If the character's count in the suffix becomes 0, we remove it from the map and decrement the suffix unique counter, as it is no longer part of the suffix. At this point, we check if the number of unique characters in the prefix matches the number of unique characters in the suffix. If they are equal, this means we have found a good split, so we increment the good splits counter. The loop continues this process for each character in the string. Finally, once the loop completes, we return the total count of good splits. This approach ensures that we efficiently calculate the number of valid splits by maintaining and updating the prefix and suffix maps dynamically as we iterate through the string. To solve this problem, we start by initializing some variables. We use prefix underscore count to keep track of the character frequencies in the left partition of the string and suffix underscore count for the right partition. Initially, suffix underscore count is populated with the frequencies of all characters in the input string, which in this case results in a 4, C1, B1. We also initialize good underscore splits to 0, which will count the number of valid splits where the number of unique characters in both partitions is equal. Additionally, we calculate prefix underscore unique as 0, since the left partition starts empty, and suffix underscore unique is 3, because there are 3 unique characters in suffix underscore count. Now, as we iterate through the string, we start with index 0, where the character is a. Updating prefix underscore count, we add a, resulting in, a 1, and increment prefix underscore unique to 1. In suffix underscore count, we decrement the count of a, leading to, a 3, C1, B1, but since the number of unique characters in the suffix remains 3, there's no good split yet. At index 1, the character is again a. Updating prefix underscore count, we now have, a 2, but prefix underscore unique remains 1 because it is not a new unique character. In suffix underscore count, a decreases to 2, resulting in, a 2, C1, B1, and again, the number of unique characters remains unchanged at 3, so still no good split. At index 2, the character is C. Adding this to prefix underscore count, we now have, a 2, C1, and prefix underscore unique increases to 2 because C is a new unique character. In suffix underscore count, C decreases to 0, so it's removed, leaving, a 2, B1, and reducing suffix underscore unique to 2. Now that prefix underscore unique equals suffix underscore unique, we increment good underscore splits to 1. Next, at index 3, the character is a. Adding it to prefix underscore count, we now have, a 3, C1, but prefix underscore unique remains 2 because it is already in the left partition. In suffix underscore count, a decreases to 1, resulting in, a 1, B1, and suffix underscore unique stays at 2. Since prefix underscore unique equals suffix underscore unique, we increment good underscore splits to 2. At index 4, the character is B. Adding this to prefix underscore count, we get, a 3, C1, B1, and prefix underscore unique increases to 3 because B is a new unique character. In suffix underscore count, B decreases to 0, so it's removed, leaving only a 1 and reducing suffix underscore unique to 1. Here, prefix underscore unique no longer equals suffix underscore unique, so no good split occurs. After iterating through the entire string, the final count of good splits is 2. Now let's analyze a different example where the input string is s equals abcd. We begin by initializing the variables. Prefix underscore count starts empty, while suffix underscore count is populated with the frequencies of all characters in the string, resulting in a 1, b1, c1, d1. Here, good underscore splits is initialized to 0, prefix underscore unique to 0, and suffix underscore unique to 4 since there are 4 unique characters in the suffix. At index 0, the character is a. Adding it to prefix underscore count, we now have a 1, and prefix underscore unique increases to 1. In suffix underscore count, a decreases to 0, so it's removed, leaving b1, c1, d1, and suffix underscore unique decreases to 3. Since prefix underscore unique and suffix underscore unique are not equal, there's no good split. At index 1, the character is b. Adding this to prefix underscore count, we have a 1, b1, and prefix underscore unique increases to 2. In suffix underscore count, b decreases to 0, so it's removed, leaving c1, d1, and reducing suffix underscore unique to 2. Now that prefix underscore unique equals suffix underscore unique, we increment good underscore splits to 1. At index 2, the character is c. Adding it to prefix underscore count, we now have a 1, b1, c1, and prefix underscore unique increases to 3. In suffix underscore count, c decreases to 0, so it's removed, leaving only d1 and reducing suffix underscore unique to 1. Here, prefix underscore unique and suffix underscore unique are not equal, so no additional good split occurs. The final count of good splits for this example is 1. Finally, let's examine a simpler case where the input string is s equals AAA. Here, we initialize prefix underscore count as an empty dictionary and suffix underscore count as 5, since all characters in the string are a. We also initialize good underscore splits to 0, prefix underscore unique to 0, and suffix underscore unique to 1 because there's only one unique character in the suffix. As we iterate through the string, we see that every character is a. Adding it to prefix underscore count during each iteration results in prefix underscore unique always being 1, as there's only one unique character in the left partition. Meanwhile, suffix underscore unique decreases by 1 after each iteration as we decrement the count of it in suffix underscore count. However, because prefix underscore unique and suffix underscore unique never match at any point, no good splits occur. Thus, the final output for this example is good underscore splits equals 0. To understand the time complexity of the solution, let's break it into two main phases. First, we have the initialization phase where we pre-compute the suffix underscore count dictionary. This involves traversing the entire string s, which has a length of n, and for each character, we update the dictionary to keep track of its frequency. Since updating a dictionary is an average O(1) operation, this phase has a time complexity of O(n). Next, we move to the second phase where we iterate through the string again to calculate the number of good splits. For each character, we update both the prefix underscore count and suffix underscore count dictionaries, adjusting the counts of unique characters in constant time. This iterative process also involves a constant amount of work per character and runs for n iterations. As a result, the time complexity for this phase is also O(n). Combining these two phases, the total time complexity of the solution becomes O(n) plus O(n), which simplifies to O(n). Now, let's consider space complexity. The primary contributors to space usage are the prefix underscore count and suffix underscore count dictionaries. These dictionaries store character frequencies, and the number of keys corresponds to the number of unique characters in the string. For strings composed of fixed character sets, like lowercase English letters, the maximum number of unique keys is constant, 26 in this case. Thus, the space usage for these dictionaries is O(1) for fixed alphabets. Additionally, the algorithm requires a few integer variables like good underscore splits, prefix underscore unique, and suffix underscore unique, which also consume constant space, making their contribution O(1). In conclusion, the overall space complexity is O(1) for fixed character sets. However, for arbitrary character sets, such as Unicode, the space complexity becomes O(k), where k is the number of unique characters in the string. Now, let's analyze the algorithm under different cases. In the best case, when all characters in the string are identical, the algorithm still processes the entire string, resulting in O(n) time complexity and O(1) space complexity. For the average case, which involves a typical random string, the operations remain the same, resulting in O(n) time complexity. The space complexity depends on the number of unique characters, which is usually small for common alphabets and remains O(1). In the worst case, where every character is unique, the time complexity is still O(n), but the space complexity could increase to O(k) for large character sets. Let's compare this optimized solution to a naive approach. The naive method would involve iterating over all possible split points and calculating the number of unique characters in the left and right substrings for each split. Counting unique characters for each split requires O(n) time, and with n1 split points, the overall time complexity becomes O(n squared). In contrast, the optimized approach avoids recalculating unique character counts by dynamically maintaining prefix and suffix dictionaries. This reduces the time complexity to O(n), making it far more efficient. To conclude, the optimized solution achieves O(n) time complexity and O(1) space complexity for fixed character sets, making it highly effective for processing large input strings. The use of dynamic prefix and suffix dictionaries is the key component that ensures this efficiency. When tackling this problem, there are a few common mistakes to watch out for. First, ignoring edge cases for very small strings can lead to incorrect results. For instance, if the string has only one character, like there's no valid way to split it. Always ensure your solution explicitly handles such edge cases. Another common error is failing to reset state variables when recalculating partitions during a sliding window or prefix-suffix approach. If variables like character counts aren't reset properly, the left and right partitions may not be computed correctly. Next, brute force implementations can be especially problematic. If you're recalculating distinct character counts for each split in a double loop fashion, your solution may end up with O(n) superscript 2 complexity, making it inefficient for larger strings. Instead, use optimized structures like hash sets or frequency arrays to speed up these calculations. Lastly, the choice of data structure matters. While hash sets are commonly used for counting distinct characters, they may not be the most efficient option. For example, when dealing with lowercase English letters, a fixed-size array of 26 elements is faster and uses less overhead compared to a hash set. Carefully consider what works best for both time and space efficiency. Another frequent pitfall is misunderstanding the problem requirements. Some participants mistakenly count the total unique characters across the entire string instead of focusing on distinct partitions. This misinterpretation leads to incorrect solutions, so always reread the prompt thoroughly to ensure you understand what's being asked. Now, when solving problems like this, sliding window techniques are often the key to optimization. By pre-computing prefix and suffix distinct counts, you can eliminate redundant calculations and significantly improve efficiency. It's also important to weigh the trade-offs between space and time complexity. For example, frequency arrays can reduce time complexity but require additional space. In an interview setting, discussing these trade-offs demonstrates a strong grasp of the problem. Clarifying assumptions early is another critical step. For instance, ask about input constraints, such as the allowed characters or maximum string length, so you can design your solution accordingly. Lastly, interviewers value incremental improvements. Even if you start with a brute force approach, discuss how you can refine it, perhaps with prefix arrays, sliding windows, or hash maps. This process highlights your problem-solving mindset, which is often more important than immediately producing the optimal solution. This problem also relates to a number of other popular LeetCode problems that you may encounter. For instance, LeetCode 3, which asks for the longest substring without repeating characters, focuses on managing distinct characters in substrings. Another example is LeetCode 76, which involves finding the minimum window substring and optimizing substring calculations with a sliding window approach. Similarly, LeetCode 340 and 159 deal with constraints on distinct characters in substrings, such as limiting the number of distinct characters to 2 or a specified value. Exploring these problems can help reinforce your understanding of substring-related techniques. Now, one alternative approach for this problem is using prefix-suffix arrays. By pre-computing the distinct character counts for all prefixes and suffixes of the string, you can calculate results in n time. This method significantly reduces the computational overhead compared to brute force. However, it does require additional space to store the prefix and suffix arrays, so you should be mindful of this trade-off when considering this approach. Another efficient method is the sliding window approach. Here, you maintain a dynamic sliding window for the left and right partitions, updating distinct character counts as the window moves. This approach is both space-efficient and fast, but it requires careful implementation to avoid common pitfalls like off-by-one errors. If you're looking for something simpler, an optimized brute force approach can also work. Instead of recalculating distinct counts for each split from scratch, you can use a hash set to incrementally update the counts as the window shifts. While easier to implement, this method is still slower for very large strings compared to more advanced techniques. Lastly, dynamic programming can sometimes be applied, particularly for more complex variations of this problem. By storing intermediate results for overlapping substrings, you can avoid redundant calculations. However, dynamic programming may be overkill for simpler versions of this problem and is best reserved for cases where it offers a clear advantage. Each of these methods has its trade-offs, so understanding the constraints and requirements of the problem will guide you toward the best solution. Great job! We've successfully solved problem number 1525 and learned some valuable techniques along the way. Remember, practice makes perfect, so keep coding and refining your skills. Thanks for watching, and I'll see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!